If you've ever watched a car drive by and wondered how fast it's going or whether it's speeding up or slowing down, you're already thinking like a physicist. Motion happens all around us, and graphs are one of the best tools we have to understand it. They turn motion into a picture so we can see what's happening over time. In physics, two of the most important motion graphs are distance time graphs and velocity time graphs. Let's break down what each one shows, how to read them, and how they connect. Start with distance time graphs. On these, time is always on the x-axis, and distance, or sometimes displacement, is on the y-axis. Distance is how much ground an object has covered. Displacement is how far it is from the starting point, and it can be negative if the object moves backward. So if you're looking at a distance time graph and the point at t equals 4 seconds is at 10 meters, that means the object is 10 meters from where it started after 4 seconds. Now, the key to reading a distance time graph is the slope. The slope tells you the speed. If the graph is a straight line sloping up, the object is moving at constant speed. The steeper the line, the faster it's going. If the line is flat, horizontal, it means the object is not moving at all. Time is passing, but distance isn't changing. That's a stationary object. If the line curves upward, the object is speeding up. If it curves and flattens out, it's slowing down. And if the graph slopes downward, only possible if we're plotting displacement, it means the object is moving back toward the starting point. That's negative velocity. Let's do a quick example. Suppose the graph goes from 0 meters at 0 seconds to 8 meters at 4 seconds. That's a straight line. The slope is 8 divided by 4, which is 2 meters per second. That's the speed. If the graph is curved, we can still find the speed at a single moment by drawing a tangent line and finding its slope. That's called instantaneous speed. But if we want average speed over a time interval, we just take total distance divided by total time. Now let's move to velocity time graphs. These are different. Time is still on the x-axis, but now velocity is on the y-axis. Velocity includes direction, so it can be positive or negative. A point at 3 seconds with a velocity of 5 meters per second means the object is moving forward at 5 meters per second at that moment. If the graph is a horizontal line, velocity is constant. If the line slopes up, the object is accelerating. If it slopes down, it's decelerating. The slope of a velocity time graph is acceleration. So if velocity goes from 0 to 4 meters per second in 4 seconds, the slope is 4 divided by 4, which is 1 meter per second squared. That's constant acceleration. But here's the big difference. The area under a velocity time graph tells you displacement. If the graph is a straight horizontal line at 4 meters per second for 5 seconds, the area is a rectangle. 4 times 5 equals 20 meters. That's how far the object moved. If the graph is a triangle, like if velocity increases from 0 to 4 over 4 seconds, the area is 1/2 times base times height. That's 1/2 times 4 times 4, which is 8 meters. That's the displacement. If the graph dips below the time axis, velocity is negative. That means the object is moving in the opposite direction. The area under the axis counts as negative displacement. If you want total distance traveled, you take the absolute value of all areas and add them up. If you want net displacement, you keep the signs. Now let's talk about speeding up and slowing down. Speed is the magnitude of velocity. If velocity and acceleration have the same sign, both positive or both negative, the object is speeding up. If they have opposite signs, it's slowing down. For example, if velocity is -4 and acceleration is +2, the object is moving backward but slowing down. If velocity is negative and acceleration is also negative, it's moving backward and speeding up. One more key idea: direction change. On a velocity time graph, the object changes direction when the graph crosses the time axis, when velocity goes from positive to negative, or vice versa. A change in slope doesn't mean a change in direction, only crossing 0 does. Now, how do distance time graphs and velocity time graphs connect? Velocity is the slope of a distance time graph. Acceleration is the slope of a velocity time graph. Displacement is the area under a velocity time graph. So if you see a straight line on a distance time graph, that's constant velocity, and it shows up as a flat line on a velocity time graph. If the graph is curved, that means velocity is changing, and the velocity time graph will have a slope. Let's do a full example. Suppose a distance time graph goes from 0 to 8 meters in 4 seconds. That's a straight line. The slope is 8 divided by 4, which is 2 meters per second. On a velocity time graph, that would be a horizontal line at 2 meters per second. Now, suppose the velocity time graph is a triangle from 0 to 4 seconds, going from 0 to 4 meters per second. That's constant acceleration. The slope is 4 divided by 4, which is 1 meter per second squared. That's constant acceleration. Let's summarize. On a distance time graph, the slope is speed. On a velocity time graph, the slope is acceleration. On a velocity time graph, the area under the curve is displacement. A flat line on a distance time graph means the object is stopped. A flat line on a velocity time graph means constant velocity. A curved distance time graph means acceleration. A sloped velocity time graph means acceleration. And when a velocity time graph crosses 0, the object changes direction. These graphs are powerful. They let us see motion, calculate speed, velocity, acceleration, and displacement, and understand how objects move. Whether it's a car on a road, a ball in the air, or a runner on a track, motion graphs help us tell the story of how things move.